Hey, this is Uwe. I'm the CTO of Image Engineering. And in this session, I'm going to give you an introduction to the DTS. The DTS is developed for the automotive industries and for the specific issues that cameras in the automotive industry have. So we collect a lot of feedback from customers, specifically from Bosch in Germany, and developed the DTS. So even though Bosch was involved or giving some or setting up their wish list, it is an entire product that is developed by Image Engineering and owned by Image Engineering, so no influence on that side. The DTS, or Dynamic Test Stand, it has a capability other than a static target like an OECF or dynamic range target or color target, that it can create the scene and can change itself. So it's a computer controlled target for cameras that also allows to obtain new KPIs that are more sophisticated than traditional ones. So we do not measure like SNR, but we measure CDP. And we can also measure MMP to describe how flicker or flickering light sources influence the performance. So these are all KPIs that are rather new developed, but have the big benefit that they can overcome the issues with traditional measurement. So the DTS has several different hardware components that allow for different measurements of different KPIs. So what you see here is the head unit of the DTS. So that's what is really the target that the camera can capture. It is designed with a so-called distortion correction. So all important components can move and adopt itself to, or can be adopted to the FOV of the camera. One very important part are the different light sources there. So 6 light sources that are used for the CDP measurement. Then all these light sources can also flicker. So for the MMP measurement, the modulated light mitigation probability. And then we have also the IQLED technology inside, so that we can create different colors to measure color separation probability. And you have moving components to see if you have some motion artifacts in your camera. So you see many different aspects are tested with these devices, and a lot of them, or most of them, are really specific and unique to the automotive environment. So for cameras, forward-looking cameras, ADAS cameras, because they really need to be reliable. Our life depends on these cameras. So the DTS features 7 white LED light sources that can also flicker and are used for the CDP, 2 multispectral LED light sources, so basically CAL2 devices. It has small single LEDs that can also be used for flickers, so for some flicker artifacts, and active mechanic viewing angle adaptation. Long word for distortion compensation. And everything is combined with a PC to touch control, so you can easily work with that. As already said, so measurements that you can perform with that is the CDP, the contrast detection probability. I will talk about that later. And the MMP is a modulated light mitigation probability. A KPI under development, also in big discussions at some standardization groups, is the color separation probability. The hardware is already there prepared and can be used. So it's also about these units. So CDP and MMP are strongly discussed within IEEE P 2020, an international standardization group to address image quality for automotive imaging. As it is with standards groups, things seem to be longer than expected or take really some time, but we hope that by end of this year, 2020, or in the beginning of 2021, there will be first publications from the P2020 workgroup that will include CDP, MMP, we'll see also with others. But we as Image Engineering are contributors to this work group. We work actively there, and we already have seen with many customers we work that these metrics do work very well, can be really a benefit for customers for using it. And we hope that also in the future this will be standardized via the IEEE P2020. The DTS has a specific workflow, so we try to adopt to the daily use of testing cameras. So it's not, so we separated the software to different tasks, so made different softwares for that. So you have a sequence generator. So with that as a software, with that you create a certain sequence for controlling the DTS. So you can say at which intensities do I want to have my light sources, at which frequencies do my light sources flicker, and what colors do I see in my color patches and so on. So then you take the information to the DTS. So the sequence generation can be done in the office or somewhere. Then you bring this to the DTS, upload it there, and that's where you actually capture your camera. So that's where you capture the images of that specific sequence. So your device under test goes into the DTS, and then the sequence will be played, so the DTS will provide to the camera the signals as defined in the sequence. So you have a 7-segment part in the center of the DTS, so that will always be captured with the images, so that that is also stored within the images that were captured by the device under test. So that's where we have the link. And then you have the DTS evaluation software. That actually does the analysis. So this software then gets the data from the DTS and gets the data from the device under test. And that can then be used to evaluate for the different KPIs I was talking about. So as said, we have the sequence generator, we have the control software, and we have the evaluation software. All of them work smooth together so that you get your results. The idea also why we separated sequence generation and evaluation software, because also some customers think about asking their suppliers to do tests, so that they get a sequence and then just ask their suppliers, okay, please run this sequence for me and give me the data so I can do the evaluation. So that's sometimes especially in automotive, where you have a heavily rely on suppliers. So no one does all imaging or all these things by themselves. It's always relying on the OEM, the tier 1, tier 2s, and so on, so that they can work together and define things. That's why we separated this in different software packages. Okay. I already talked about CDP. I want to give you a quick introduction to that. So there are several publications also from image engineering. You can find that on our website. We did give a talk at the Electronic Imaging Conference, and so there are some background papers about that. And as said, we hope that the IEEE P2020 will have official documents out rather soon. But I give you the introduction here to CDP. So why CDP? So what CDP wants to do is the contrast detection probability. So it wants to say, how well can a camera capture a certain contrast? And so we assume that a contrast of a certain object, so object to the background, for example, is a key performance indicator for the camera, that it can detect an object. So you see here different examples where in the top row, so you have some traffic lights in the background, but due to some fog, the contrast is reduced. But the question is, how much contrast loss can the camera handle? So it is obvious that on the left, in the top left, it's a high contrast. Every camera should be able to do that. But if there is fog or other environmental influences, they will reduce the contrast. The question is, can my camera still then see that object? So that is where CDP can help. Also, you see in the lower right effects where strong HDR is introduced to or is used to be able to image the the tunnel region and the outside region, which creates a huge contrast. The problem is some cameras might completely lose that, some might introduce that, but also then these cameras that do have the HDR might show some certain artifacts. So you see here that the white traffic line suddenly becomes black. So that's a huge problem if your line detection algorithm depends on having a white line on a dark background. So these are things that can be tested. So why do we need a new metric? I mean, there's SNR out there, but if you have some experience in this field, you know that SNR does not really tell you everything. One big problem that we have is, as we do have HDR in automotive, so we combine multiple images, we also have these so-called SNR drops. So especially in the regions between, when you go from one image to the other from the HDR, you have SNR drops. So the SNR goes down, and you will actually see that in the image. So you have a non-continuous SNR curve, and these SNR drops can really cause some trouble in detection. So the SNR curve itself is not really able to describe these things, and also the dynamic range is a problem to describe, because dynamic range will only be from the further right to the complete left, so the darkest to the brightest, but what happens in between is not really described in dynamic range. So that's where CDP, or especially the CDP map, is something which is very useful. So these are one effect that you see here from an SNR drop. So you have these bright to dark gray patches, but the bright patches show significantly more noise than the dark patches, which is counterintuitive to a single exposure from it. But here it is because the bright part of that patch comes from another exposure than the dark region. So other effects that can reduce contrast are glare or flare from like pollen dust and things. So the question is always, can my camera still detect the car even if the contrast is reduced due to glare in this example? So to do the measurement on that, we provide different gray patches to the device on the test. So inside the DTS, we have 6 light sources in there. Each of them have 36 gray patches. So that means that we have 218 gray patches, and from that we can always create pairs. So in this example, we have patch A and patch B. So they have a known contrast in luminance, and then we can sample all the pixels from these A and B and create the probability density function from the difference from A and B. So how do we do that? Basically, we do a random pairing. So we take 1 pixel from B, subtract that with 1 pixel from A, and that is then 1 point in the probability distribution. And we do that over and over again, so that we have, after that, we have many, many, many pixels compared, so that we get a distribution of the difference between A and B. And then, so with this random pairing mechanism, we can create the probability density function. And then we can say we want to say how many values fall within my predefined confidence interval. So I say, okay, for my application, I need a certain contrast, or I need a certain difference. So I can say, I need this difference in these boundaries. And then we can calculate. So the CDP is actually the amount of values that fall within the confidence interval. So a CDP value of 100 means all are in confidence, all are good. So I have 100% probability that these 2 patches can be differentiated. And if the lower the CDP, the worse it is. And CDP that can then be influenced So you get a low CDP either because of noise or because of a tone curve variation, so that two patches move to each other, or that one patch gets noise, the other one has some other artifact, and so on. So it doesn't really matter what it is. It is agnostic to the underlying model. It just tells you, can this camera differentiate these two patches? And that's the beauty of CDP. It is agnostic to all assumptions behind that. It just tells you, can I differentiate this? So as I said, we have 218 gray patches, but that might not be even enough. So we can also collect data over time. So we can change the intensity of light sources, and we just capture more and more images. So with that, we can create many, many different contrasts. We can create many different luminances and sample the data. So one comparison of one pair gives you one CDP value, and we can then combine a lot of them so that we get to a 3D mostly it's used the 2D map, so that we have on the x-axis we have the luminance, on the y-axis we have the contrast, and encoded in color we have the CDP value. So that is, and the better the CDP value, the better or the higher the probability. So in this example, the yellow area means, okay, this is a contrast or a luminance range that the camera can test or can reproduce very well with 100% probability. But it gets into the orange or into the darker colors, it means there we have some problems. It cannot do that. And it's quite intuitive. The higher the contrast, the higher the luminance, the better the probability. And if I get into low contrast, low luminance, my CDP gets worse. And with that, we have some lines in there. So even if I have like multi-exposure HDR, we will see the regions between that. So instead of an SNR drop that I cannot really define, I see really regions where I lose information. So very powerful tool to evaluate camera, to see the performance, and to validate also a camera. So many customers, what they do, they have a certain sensor configuration and they want to know, okay, is this sensor configuration really doing what I want to do? And then they go to the DTS, they test the CDP for the sensor configuration, and they might see some, or if they see some issues, they try to solve it. So missing codes, so some overlap, mitigation problems, and so on. And when that is finished, then they go driving, testing the camera in the outside world. But with all these tests that have then been done before in the DTS, they can save a lot of miles, because many issues they would normally just experience in driving, they will already see in the lab. So that means feedback from customers is that with the DTS, they could reduce the test driving a lot. And that is having people driving around thousands and thousands of miles or kilometers is really something that costs a lot, that's time consuming. So with the DTS, you can do that much faster. Another test that we do is the MMP. So MMP is actually the modulated light mitigation probability. So it addresses a problem that you can see here. So the traffic light that you see there with the 80 speed limit is using pulse width modulation. It's LED based. And if you have now a short exposure time from your camera, you run into problems to render it properly. So you get this black. So that is, of course, a problem, this flicker. So you want to measure how well can my camera handle it. And more sensors nowadays have a flicker mitigation. So they have a technology in the sensor that is supposed to suppress artifacts. Or these are kind of artifacts where you have like a banding effect due to flickering light sources. So to test that, we can also use the DTS, and there we use the modulated MMP. So just to quickly explain what the problem is, if the light sources that either illuminates a scene or that you directly see uses PWM to control LED intensity. So PWM, pulse width modulation, means that you basically turn on and off your LED very quickly to control the intensity. But if you have bad luck or have very short exposure times, it can happen that your capturing, or the frame that you capture is not fully filled with one pulse from the pulse width modulation, so that you actually run into the gap between the pulse. So then you get artifacts like this bending, or like not seeing something at all, because you are always sampling in the edge, or in the gaps between the pulses of the pulse width modulated light source. So to measure this, we use MMP. So basically, we take a single pixel and track that pixel over many frames. So we capture a lot of frames, and then we track the digital value of that pixel. And if you have some bending or some flickering and so on, you will always have that you have some regions that go up, that go down. So that will show you a certain pattern. So no flicker at all would just mean you have a straight line. If you do have some flickering or bending effects, you will have certain regions where it goes up and down, the values. If they go up and down, we basically get two regions where we have two distributions of digital values. And then we can use the same technology as we have in CDP, so that we compare these two distributions to calculate the MMP. So with that, we have an indicator how well does the flicker mitigation work. And we can do that depending on frequency, duty cycle, phase. So that all influences the performance, and that should all be tested. So if you are not in the right phase, you might just not see any effects, but your user or the driver of the car will actually see that. So that's why it needs to be done. Also, frequency and duty cycle need to be tested, because just because one frequency does not show flicker does not mean that all other frequencies do not show that. So that's why the DTS is designed to show you, or gives the possibility to test different frequencies, different duty cycles, different phase, to analyze the MMP for that. Okay, so thanks a lot for watching this video. I hope I gave you a short introduction to the DTS, and I triggered your interest in that. So we are happy to provide more details and discuss your specific need with that, with our team worldwide, with our office in China specifically, if you with our team in China as well. So thanks for watching, and then talk to you soon. Thank you.